Hey everybody, welcome to another lesson in Science 24 in the chemistry unit. This is a big lesson. This lesson here we are going to start talking about the types of chemical reactions, word equations. We're going to go into formulas for common compounds, and then we're also going to just get into how to write them out, how to identify. So sit back, relax. You're here with Mr. Adamson, and I hope you enjoy. So first thing we're going to hit on is word equations. Now word equations, so to describe many different chemical reactions, chemists use a method known as a word equation. They indicate what changed during the chemical reaction and what was produced. There are a simple way for chemists to describe chemical changes and also help us recognize patterns that many reactions have. And the way that we do this is we identify all the reactants on the left, and we identify all the products on the right hand side of a reaction. Now writing word equations. So word equations always have the same format or look, and as I said right here, reactants are on the left, products are on the right. An arrow, points from the reactants to the products. So you might also see an arrow when you're reading something. An arrow can be indicated by the word produce or create. All reactants and products are separated by a plus sign. So when you're looking here, we have a plus sign, a plus sign. You will also see when you're writing and you're reading, you'll see the plus sign maybe also identified as an and. So for example, we have down here zinc, plus sign or and, hydrochloric acid, arrow. So arrow points from reactants products, produces zinc chloride and hydrogen gas and energy. So if we go then to reading it, the equation is read as zinc and hydrochloric acid produce zinc chloride and hydrogen gas and energy. Now, next thing we're going to go on to is the types of reactions that we will see. Now there are 4 types of chemical reactions that we are going to identify in this lesson. Number 1, so we're being right here, simple compound reactions. And this is where we will have element 1, so from our periodic table, element 2, and they are going to produce, so they are in our reactant side, they are going to produce the products or some sort of compound. The next type we are going to have is the exact opposite of a simple composition reaction, and this is a decomposition reaction. So decomposition reaction. And this is where we'll start with a compound, and we are going to break it apart and produce element 1 and element 2. And just remember again that these two are opposites of each other. Now the next type of reaction that we are going to have here is a combustion reaction, and this is where you are going to get right here, a CXHX, and those X's can be any number, so they could be a 1, a 2, a 3, a 4, whatever, plus oxygen, so O2, which is most likely oxygen gas, and it's going to lead us to producing CO2, which is carbon dioxide, and H2O, which is water. Now, one thing that I want you to be aware of here, CX and HX are known as hydrocarbons. And then the last type of reaction that we are going to have is a neutralization reaction. This is where we are going to, and we talked about this in a previous lesson, where you have an acid and a base coming together, and then they are going to produce salt and water. Now we're just going to talk a little more about these reactions, give you a little more examples here. So starting with the simple combustion reaction. So first one here, first point, we're going to have 2 or more elements combined to form a compound. So remember before where it said A plus B is going to give us or produce AB. Now whenever you see 2 elements as reactants and a compound as a product, you know the reaction is a simple combustion reaction. Now, most of these are exothermic in nature, meaning they release energy. And a good example of this could be hydrogen plus chlorine is going to give us hydrogen chloride, also known as HCl, hydrochloric acid. Next one we have here is a simple decomposition reaction. This is where a reaction breaks a compound into its elements. Again, simple decomposition and simple combustion reactions are exact opposites, so they're just going to flip. Most decomposition reactions are endothermic, where energy is needed to drive the simple decomposition reaction, so to move it forward, to do what it's got to do. And an example of this is electrolysis, so water breaking apart. So you have water, and if you have an electrolysis reaction, you're going to actually apply energy to it, so you'll have an electrode within the water, and you'll have the hydrogen and oxygen split apart, and you'll actually see on the two electrodes that you apply in the water, you'll see hydrogen bubbles and oxygen bubbles. Next reaction here, we have a combustion reaction. Combustion also means burning. A combustion reaction always occurs in the presence of oxygen, so it will not happen without oxygen, and always produces carbon dioxide and water. Now, I cannot stress that enough. Whenever you see the products of carbon dioxide and water, so CO2 and H2O, you know that you are dealing with a combustion reaction. So burning a candle or burning fuel in a car are two examples of a combustion reaction. Anything that you most likely is probably going to see that's not anything, but a high chance of something that is being broken apart, and you are going to have, especially like I talked before, a hydrocarbon. You are going to have a combustion reaction. So an example here, we have butane plus oxygen leads us to producing carbon dioxide, water, and energy is giving off. And as we said, that burning, that exothermic reaction. Last reaction that we have here that we're going to talk about is a neutralization reaction. A neutralization reaction occurs when an acid and a base combine to form salt and water. Now, a perfect example of a neutralization reaction is taking an antacid tablet for heartburn. The antacid is a base which neutralizes the acid in your stomach, causing the burning in the first place, and it's going to produce salt and water. So example here, within our stomach, we have our hydrochloric acid within our stomach, HCl. We take our antacid, which is NaOH, or sodium hydroxide, and we are going to produce a salt. And a salt, better known as, and get used to seeing that, NaCl, and then of course water. Next section here, formulas for common. So chemical names and formulas. So some scientists speak many different languages, and this is why they created a common language that allow for them to communicate with each other. In a word equation, we use chemical names to represent the reactants and the products. So for example, right here in the word equation, sulfur and zinc chloride produce zinc sulfide. Sulfur, zinc, and zinc sulfide are chemical names, and those are universal again, so everybody speaks the same language. Now, most chemical compounds are named according to the elements that they contain. So, for example, this compound right here, zinc sulfide, as we see it, it's composed of sulfur and zinc, and therefore it's called zinc sulfide. Now, information about the chemical composition and the structure of a compound is given by its chemical formula. An example of that would be water, H2O. So what could we say about water? How do we know about its chemical compound? Well, we can tell right here, because of this little 2, that there's 2 hydrogens, and if there's no numbers back behind the oxygen here, it's given that there is 1, and therefore we know again we have 2 hydrogens, 1 oxygen. Now, states of matter. Chemical formulas also show the state the compound is in. There are 3 states of matter that we need to be concerned about. First one here, we have a solid, which is represented by a little s. We have a liquid, which is represented by a little l. And we have a gas, which is represented by a g. Other thing that you may see sometime is AQ, and this was an aqueous solution. and that's going to be it's going to be kind of cloudy, might have a precipitate in it, almost like kind of maybe thicker. It's kind of between a liquid and a gas here. Now the chemical formula for water, H2O, can be represented in all three states, and that's something that's very special about water, because as a solid, we know it as ice; as a liquid, I mean, that's the form that we drink; and then as a gas, that's water vapor or steam. Now, naming compounds. When naming compounds, you always name the metal first and the non-metal second. So this is when we are talking about, though, specifically ionic compounds. Ionic compounds have a metal and a non-metal in them. Metals are listed first, non-metals are listed second. And if you remember on your periodic table, there's that thicker dark staircase that goes through metals on this side, and on this side here we have our non-metals. Now, a couple things to be concerned about when we're naming. You keep the full name of the metal. However, the non-metal, you change the ending to "ide." So for example, we're given the chemical name MgO. Well, Mg, it's going to be on our periodic table here on the right hand side. So it is a metal, and its name is magnesium. So we don't change it at all. We do not change the name of the metal. O, however, is a non-metal, which is going to put it on the right hand side. And I believe I just said previously that it's this Mg being a metal is on the right hand. However, I meant it's on the metals are on the left hand side. Okay, left hand side. So back to oxygen. Oxygen is a non-metal on the right hand side over here of our periodic table. And we are going to change the ending of oxygen to "ide." So if we go through this process, we name the metal first, which is magnesium, and then we take the second element here, the oxygen, and we change the ending to "ide." And therefore, instead of calling it magnesium oxygen, it's called magnesium oxide. Now, some common names. Now, not everyone is a scientist, so many chemical compounds are often called by their common name. These names are easier to use and were around long before a chemical naming system was ever created. Some examples that we may see: sodium chloride, which is NaCl, because Na is sodium, Cl is chlorine off our periodic table, but again, it's an ionic compound, so we change the non-metal, change the ending to "ide." It's also known, though, as salt. Ethylene glycol, CH2H6O2, just simply known as antifreeze. Carbonic acid, H2CO3, it's known as club soda. Okay, how about water? Well, we know water as H2O. Water is actually dihydrogen monoxide, but we better known as water. Okay, so there is some of the common names that we use within chemistry. Next section, chemical. Now, first thing that we want to talk about, though, before we get into that, is the law of conservation of mass. This is a very important law that you'll need to be aware of. Antonio Lavoisier, so I mean, you don't need to know the date, but back in the 1700s, placed a carefully measured mass of solid mercury 2 oxide in a sealed flask. Now, when heated, the compound produced liquid mercury and oxygen gas. He found the total mass of the products was identical to the total mass of the reactants. So just to see the chemical equation for Lavoisier's experiment here, he had solid mercury oxide with 10 grams, oxygen gas at 0.7 grams when the reaction went through and produced the products, and then liquid mercury, there was 9.3. We add up 9.3 plus 0.07 and we get 10, just like we started here at the beginning. So from this reaction, he concluded that the atoms in the chemical reaction were just rearranged not destroyed. So in a chemical reaction, we're producing something new, but we're not destroying what we started with. So this led to the law of conservation of mass, which states that in a chemical reaction, matter is not created or destroyed. If reaction starts with 10 grams of reactants, it will end with 10 grams of reactants. So think of those combustion reactions where you have a hydrocarbon and you have oxygen and something starts on fire. Well, you're also going to have oxygen given off. You're going to have that carbon dioxide. You're going to have that water. So, I mean, you're still going to have the same mass on the same side of the products. Now, balancing a chemical equation. Now, this is a super important slide that I want you to pay attention to. In a balanced chemical equation, the number of atoms of an element on the reactant side is equal to the number of atoms of the same elements on the product side. So I want you to think of it like ooh, that's a bad triangle, like a teeter-totter. When you are, sorry, let's redraw that. Okay, we're back. I deleted that. So let's start with my teeter-totter again here. Nope. So I have a teeter-totter. Now I have this person on this side and this person on this side. Now, in balancing a chemical equation, we want each person to be exactly at the same level on each side. That means they are balanced. So just like atoms, it has to be the same on each side. We cannot have a teeter-totter that is going to be like this, where it's heavier on one side than the other, because according to the law of conservation of mass, it needs to be equal. It needs to be balanced. So steps to balancing a chemical equation. So first one here, list the elements on each side of the arrow and count the number of atoms of the element. And we'll go through an example here. Number 2, if the equation is not already balanced, add coefficients in front of the elements or compounds one at a time. Continue until the equation is balanced. And 3, leave oxygen and hydrogen atoms until the end. So whenever you see hydrogen or oxygen in a chemical equation, balance them at the very end. So for example here, first step, list the elements on each side of the arrow and count the number. So what I suggest you do is you draw a little line here. Let's move our slide here. So we have, see our steps. So we have carbon plus O2 gives us carbon dioxide. So I suggest draw a little line. First thing, we have oxygen. We want to leave hydrogen and oxygen till the end, so we're going to start with our carbon here. So I have 1 carbon. There's no numbers listed right here, so it's given that I have 1. Now I go to my product side over here. I have only 1. There is no little number listed down beside it. If there's a little number, these are known as subscripts. If they're down on the lower half of my elements here, or compounds, they're known as subscripts, and they only apply to directly what's in front of them. So this 2 here would only apply directly to this oxygen. So in this case, again, to my carbons, there is no little numbers, so it's given that I already have 1. Next thing I go to is to my oxygens. I have a little 2, so it's given that I have 2. Now I go over here to my oxygens. This little 2 again only applies to this oxygen, so therefore I have 2. So coming back to this here, since there's 1 carbon atom and 2 oxygen atoms on the reactant side of the product, 1 carbon atom and 2 oxygen atoms on the product side of the equation, this equation is balanced. Now, last thing that I want to do here, I'm just going to move this again, show you an equation where it talks about moving large coefficients. So let's say I have hydrochloric acid is going to decompose into hydrogen gas plus chlorine. So first thing I want to do is start with anything that is not a hydrogen or oxygen. So I'm going to start with my chlorine. And again, I have no little numbers here, so it's given I have 1. I go to this side. It is given that there's no little numbers here, so I have 1. Then I go to my hydrogen. I have no little numbers here, so it's given I have 1. I go to my hydrogens here. I have 2, however. Now I compare my numbers. 1 Cl, 1 Cl. 1 hydrogen, 2 hydrogen. That is not balanced. So it said I can only add large coefficient numbers in the front, which means where these lines that I just drew, I can only put numbers there. So in this case, I need my hydrogens to be the same. So if I have 2 here right now, I need to have 2 on this side over here. So I'm going to put a 2. Therefore, that gives me now 2 hydrogens. And I still have 2 hydrogens. But something special about these large coefficient numbers, they apply to the whole chemical compound that they're in front of. So that also means now that I have 2 chlorine. If I look over here, I only have 1. So what can I do? I can put a large 2 in front of that chlorine to give me 2 also. Now when I go back to compare, 2 hydrogens here, 2 hydrogens here, 2 chlorine here, 2 chlorine here. Therefore, I have a balanced chemical reaction. All right, that was a lot of information. I hope you enjoyed. Thanks for listening.